Hi everyone, welcome to week 3 in review. So this time we're going to review Jordan Canonical Form instability. We already reviewed this in the last week in review, but it's a complicated topic and it bears repeating. And then we're also going to talk about discrete time, linear time invariant systems. So let's start with Jordan Canonical Form. So the basic result here is that for any n by n matrix A, no assumptions on the matrix, there exists an invertible matrix T such that TA, T inverse, is a matrix in Jordan form. And what that means is, first of all, that it's block diagonal. So J consists of blocks J1, J2, J3, all the way up to JK. And as we've discussed in class and in the previous reviews, each J, I, has the same value all along the diagonal, and then one's on the off diagonal. So let's see an example of this. So let's suppose that A is equal to the matrix 3, 2, 1. 2, 3, 4, 1, 4, 3. What is the Jordan canonical form of A? Well, we haven't discussed in the general case how you find the Jordan canonical form, but in this case, we know how to do it. So we observe that A is symmetric. A is symmetric. And what we know about symmetry is that if A is symmetric, this implies that A is diagonalizable, which implies that all the Jordan blocks are 1 by 1, which implies that J is just equal to the matrix that's diagonal and has the eigenvalues on the diagonal. So I just made up this matrix A, so it's not going to have nice and clean eigenvalues. So if you go to MATLAB and you press EIG of A, you'll find that the eigenvalues, again, maybe they have a better expression in terms of radicals, I'm not sure, are minus 1.1394, let's call this lambda 1, 2.2151, let's call that lambda 2, and 7.9243, let's call that lambda 3, and that means that its Jordan canonical form is equal to these values, lambda 1, lambda 2, lambda 3. Now you can check this by asking MATLAB directly to compute the Jordan form by writing Jordan of A, and you'll see that indeed this is the Jordan canonical form. So what about stability? What can we say about this? Well, we know that we see that lambda 2 is in the right half plane and lambda 3 is in the right half plane. So this means that it is unstable. Let's look at a different example that's not symmetric. So let's look at the 4 by 4 matrix A, which is equal to 1, 2, 0, minus 4, 0, minus 2, 2, 2, 0, 0, 3, 4, and 0, 0, 0, minus 1. What is the Jordan canonical form of A? Well, again, we haven't discussed how to compute Jordan canonical form for an arbitrary matrix, but this has something special about it. So we have this other fact that if all the eigenvalues are distinct, then a matrix is diagonalizable. So remember that we discussed this as just a fact before, but this is implied by Jordan canonical form. Because if all the eigenvalues are distinct, then that means that there must be, for a 4x4 matrix, 4 blocks. Because we know that the eigenvalues are what's on the diagonal of the blocks. And the only way to make 4 blocks for a 4x4 matrix is if they're all 1 by 1, which means that they are, again, diagonalizable. And so this means that Jordan Canonical Form, see, this is upper diagonal, so it's easy to, upper triangular, so it's easy to just read off what the eigenvalues are. These are all distinct, so therefore the Jordan Canonical Form must be this. So let's, so again, is this stable? No. This is also unstable, because the real part of lambda 1 and the real part of lambda 3, these are all positive, so they're in the right half plane. So let's look at another example that's very similar, also upper triangular. So let's look at the matrix A. I'm just going to make one difference in the one change. So it's 1, 2, 0, minus 4, 0, minus 2, 2, 2, 0, 0, 1, 4, and 0, 0, 0, minus 1. So what can we say in this case? What is the Jordan Canonical Form of A? Again, there is always a unique Jordan Canonical Form up to rearranging of the blocks, but we haven't discussed how to compute it. So what do we know about this? It's not symmetric. Of course not, it's upper triangular. And also, the eigenvalues, we can read these off because it's upper triangular, are 1, minus 2, 1, minus 1. So that means that there's a multiplicity here. So we don't know, or we haven't discussed in class how we might find the Jordan Canonical Form of this matrix. So here's something that I would ask you. In fact, I did ask you in the homework, but here's something that I would expect that you could answer, which is, what are possible Jordan Canonical Forms of A? So this is an easier question than asking you to compute the Jordan Canonical Form. Again, that's possible. There's only a unique answer. You can find that with MATLAB, but we can't. But we haven't learned the techniques to do that. So I wouldn't ask that much. So what are the possible forms? Well, again, we know that J has to be block diagonal. So how many blocks could we possibly have? Well, we know that one option is to have 3 blocks, and another option is to have 4 blocks. How do we know that we must have at least 3 blocks? Well, each block has to have the same elements on the diagonal, and there's 3 things that have to go on the diagonal: plus 1, minus 2, and minus 1. So this means that there are at least 3 blocks. And of course, there could be 4 blocks. So the 2 options are 1, 1, minus 2, minus 1. Remember that the ordering does not matter. So this would be 4 1 by 1 blocks. And the other option is 1, 1, 1, minus 2, minus 1. So this is 3 1 by 1 blocks, and 1 2 by 2 block. So you can go to MATLAB and check which is the answer. And all you need to do is write Jordan of A. And you'll find that in this case, it's the second example. So it turns out that this is the true answer. So is this stable or unstable? Well, it is unstable because the real part of lambda 1 is positive. Okay, so that's a brief review of Jordan Canonical Form. Now let's talk about discrete time, linear time-invariant systems. So discrete time, linear time-invariant systems. So here, instead of differential equations, we're thinking about difference equations. So something like q of k plus 1 is equal to, this is an example, is equal to q of k minus 5 q of k minus 1 plus 3 q of k minus 2. This is an example of a discrete time, linear time invariant system. It's discrete time because time is discrete, and it's linear and time invariant because, for the same reasons that a differential equation was linear and time invariant. So it's linear in all the q's. So you have a q of k minus 1, but you never see a product of these or a square of these. And it's time invariant because the coefficients don't depend on time. So the coefficients are time independent. And so what we said in class is that just as for differential equations, we can transform this to x of k plus 1 is equal to a times x of k, where now x is a vector. So we have this, we start with a difference that requires a difference. In order to update q, you need to know not only the current time, but you need to know the previous 2 time steps that's in this example. And we can convert this to just having a difference equation where if you know where you are right now, then you can update. And we do this by adding dimension to the state. So for this example, for the above example, we could set, say, x1 of k to be q of k, x2 of k to equal q of k minus 1, and x3 of k to equal q of k minus 2. And so what do we get in that case? We get that x3 of k plus 1 is equal to q of k minus 1, which is just x2 of k. x2 of k plus 1 is equal to x1 of k. And what about this one? x1 of k plus 1. Well, this is equal to q of k plus 1. So this is equal to, by the recursion above, q of k minus 5 q of k minus 1 plus 3 q of k minus 2. And I want to express this only in terms of x1 of k, x2 of k, and x3 of k. So this is equal to x1 of k minus 5 x2 of k plus 3 x3 of k. That's what goes in this box. And therefore, I have now the expression x of k plus 1 is equal to the 3 by 3 matrix what goes here. So x1, here, let me be more clear here. This is x1 of k plus 1, x2 of k plus 1, and x3 of k plus 1. So x1 of k plus 1 is equal to 1 times x1 of k minus 5 times x2 of k plus 3 times x3 of k. x2 of k plus 1 is equal to 1 times x1, 0 plus 0 times x2 plus 0 times x3. And x3 of k plus 1 is equal to 0 times x1 plus 1 times x2 plus 0 times x3. So I've got x of k plus 1 is equal to a times x of k. So just as we did with continuous time systems, we can ask about stability. So let's start with the scalar case, exactly like we did in our development for different differential equations. So if I have x of k plus 1 is equal to a times x of k, well, this is equal to a squared times x of k minus 1. And I can keep using this recursion down to, I'll have finally a to the k plus 1 times x of 0. So in general, I've got x of n is equal to a to the n times x of 0. And you can see that this is the same as precisely true when I have x of k plus 1 as a vector is equal to a times x of k. I have x of n is equal to the matrix a raised to the nth power times x of 0. And our challenge, just like with continuous time, linear time invariant, we had x of t, the vector, is equal to e to the at times x of 0. And our challenge was to understand what is e to the at and what are stability properties of it. And for that we used the matrix exponential. I'm not going to review that in this little review. So how do we compute a to the n? Well, let's again start. So if a is a scalar, then of course, then we know that a to the n is just a scalar to the n. So for stability, we need the magnitude of a to be strictly less than 1. What if a is diagonalizable? And I'm developing things exactly like we did for continuous time. I'm just mirroring it. Conceptually, we're just mirroring that precisely. So let's suppose a is diagonal, sorry, not yet diagonalizable. So a is equal to d1, d2, all the way down to dn. Well, it's not difficult to see that a to the n is equal to d1 to the n, d2 to the n, I shouldn't overuse n here, dm to the n. And therefore, for stability, we need each di to be strictly less than 1. This symbol means for all. What about diagonalizable? That's the next most complicated. Diagonalizable matrices A. So that means that there exists an invertible matrix T, so that TA T inverse is a diagonal matrix, which is the same as writing that A is equal to T inverse times D times T. And again, as we did this exact calculation. We found that A squared is equal to T inverse dt times T inverse dt. The T's cancel and we get T inverse D squared T. In general, A to the n is equal to T inverse times D to the n times T. So if A is diagonalizable, for stability, we need all of the di's to be, again, strictly less than 1. And what are these di's? These are nothing else than the eigenvalues of A. Now what about the general case? Let me check my numbering. We're up to 4 here. Okay, so for the general case, we have to use, again, Jordan Canonical Form. So we know that there exists a matrix T that's invertible, so that TA T inverse is equal to J. Again, this is the same as writing that A is equal to T inverse times JT. This means that A to the n is equal to T inverse times J to the n T. So if you're not sure how I got this, you should check that. It's using very similar reasoning as we did above. So now all we need to do is understand what is J to the n. Well, J, again, is block diagonal, J1, J2, all the way down to JK. And you can check, in fact, we've done this in class, that J to the n is equal to J1 to the n, J2 to the n, all the way down to JK to the n. So therefore, all we really need to understand is what is Ji to the n. So if Ji is a 1-by-1 matrix, that means that Ji is just equal to lambda I. So then, of course, Ji to the n is equal to lambda I to the n. If Ji is a 2-by-2 matrix, then Ji is equal to lambda I, 1, 0, lambda I. And what is ji to the n? We discussed this in class, and we used the binomial formula. So we used in class the fact that a plus b to the n is equal to the sum from k equals 0 to n of n choose k, a to the n minus k, b to the k. And we're going to apply this to ji, which I'm going to write as lambda times the identity plus the matrix 0, 1, 0, 0. And I'm also going to note, so this is going to play the role of A, and this is going to play the role of B in the binomial expression above. So I'm also going to note that B squared is equal to B cubed in all higher order powers, which is just the zeros matrix. And this is going to simplify the binomial. This means that the binomial expansion is only going to have two terms. So ji to the n is equal to lambda I plus 0, 1, 0, 0 to the n, which is the sum that I've written above, except it's only going to have the first two terms. So it's going to be n choose 0 times lambda I to the n plus n choose 1, whoops, I ran out of space, I'll write that below, plus n choose 1 times lambda I to the n minus 1 times this matrix to the 1. And this is equal to the matrix lambda to the n times I plus n times lambda to the n minus 1 times the identity times 0, 1, 0, 0. And writing out what this is lambda to the n times lambda to the n minus 1, 0, and lambda to the n. And something similar happens for a 3 by 3. So what do we need for stability? And stability, of course, here is as n goes to infinity. So if lambda is strictly less than 1 in magnitude, then lambda to the n and also n lambda to the n minus 1, both of these go to 0. And the reason is that if lambda is less than 0, this decays exponentially quickly, and this grows linearly. So that means an exponential decay is going to beat out linear growth. On the other hand, if lambda is bigger than 1, then everything goes to infinity. So we have that this is unstable. Meanwhile, if lambda is actually equal to 1, this is the border case, then again it's going to be unstable. And why? It's going to be unstable because of this term n times lambda n minus 1. Because in the magnitude of this, the magnitude of n times lambda to the n minus 1 is just equal to the product of the magnitudes. So it's going to be equal to n times the magnitude of lambda to the n minus 1, which is just equal to n, which goes to infinity. And so finally we concluded by giving the stability rules for discrete time, linear time-invariant systems. X of k plus 1 is equal to a x of k. We had that it's stable if the magnitude of every eigenvalue is less than 1. It is unstable if the magnitude of lambda I is greater than 1 for even a single eigenvalue, lambda I. And if the magnitude of lambda I is equal to 1, if they're less than or equal to 1 for all I, if you look at an eigenvalue that's equal to 1, then if the corresponding Jordan block is 1 by 1, then it's marginally stable or neutrally stable, which means it's not going to infinity and it's not going to 0. On the other hand, if the Jordan block Ji is 2 by 2 or bigger, then it is unstable. We'll continue on Tuesday.